This is Chapter 2, Chemistry of Outer Transition Elements, that is part of Inorganic Chemistry, and we are studying the general properties of the transition elements, that is for the D block. And from this topic, we will study today the color complexes that by transition elements form color complexes. Talking about the transition metals, as it is a metals and we know that metals are electropositive, so it is an cation. When a transition metal interacts with the ligand, ligands are electron pair donors, so either they are negative or neutral. This interaction leads to the splitting of the 5 degenerate d orbitals into two sets of energy levels, which is T2G and EG. T2G is the lower energy level, EG is the higher energy level. In this image, you can see that you have a center atom which is transition element that is surrounded by the ligand. Now how the d orbital splitting takes place into two energy levels for the 5 degenerate d orbitals? When the transition metal and ligand interacts, their 5 degenerative orbitals are splitted into higher energy level and lower energy level. The lower energy level is called as T2G, which consists of 3 splits, which is dxy, dyz and dxz. The higher energy level is Eg, which consists of 2 splits, that is dz square, dx square and y square. Here you can see that you have a difference of energy between the higher energy level and lower energy level, or you can also say that we have an energy difference that is between Eg and T2G. Keep in mind that this is an octahedral ligand field. This energy difference for the octahedral splitting is called as the crystal field splitting, and it is denoted by the delta naught. This image shows the image of 5 degenerate d orbitals into T2G and Eg energy level. Now how does transition elements show colored? When the incoming light strikes the electrons get excited and they move from the lower energy level, that is T2G, to the higher energy level, which is Eg. Keep in mind that we are talking about the interaction of the transition metal and ligand. For the jumping of electron, excitation of electron, energy is absorbed of a specific wavelength. And we know that this excitation is an unstable state, so then energy is released. This energy is released in the form of light. Remember that the transmitted light color is the color we see. For example, if the transition metal solution is of yellow color, it means it is transmitting the yellow colored light. This is an example of the tetraamine titanium ion, and the complex of tetraamine titanium ion is green in color, which means that the transmitted wavelength for this complex lies for the green color. Now the explanation how you can write this in your wording. When the visible light falls on the sample of the transition metal complex, what happens that the electrons absorb the light and jump from lower energy level to the higher energy level. This absorb corresponds to the energy difference between D to D transition. Why D to D transition? Because we are involving the splitting of the d orbitals. So D to D electronic transition will take place. When the electronic transition takes place, the remaining of the wavelength of the light, it is then transmitted, which gives the characteristic color to the complex. Here you can see that this is an image that shows the color of some transition metals ion for titanium, chromium, manganese, iron, cobalt, nickel and copper. These are transition metals. It means the basic reason for them to form colored complex is the same, which is the D to D electronic transition when it is interacted with the ligand. But here you can see that different transition elements show specific color of the solution. What is the reason behind it? The reason behind it is that this color depends on two factors. Number one, that is the oxidation state of the metal ion. As transition elements show variable oxidation state, it means if the oxidation state is changing, the color of the complex will also change. Second is the nature of the ligand. The ligand that you are using, what is the nature of that ligand? So these two factors affect the color of the transition metal complexes. One thing that you must remember that for D to D electronic transition, you need unpaired electron. It means if a transition element has unpaired electron, then it will give color. And if you remember, for magnetic behavior, we studied that there is one element in the 3D series that lacks unpaired electron and has no unpaired electron, and that was zinc. It means in zinc, since it has no unpaired electron, so there will be no D to D electronic transition. Ultimately, zinc complex will not give any color and it is colorless. There is no specific color of it. You get this in your reasoning for 1 mark, that why the zinc ion complexes give no color. So you simply write that it has no unpaired electron, so there is no D to D electronic transition possible here. Now the question, why tetraamine copper is blue but tetrahydroxyzincate is colorless? What is the reason? The reason is same. In zincate complex there is no unpaired electron. All electrons are paired, so there is no D to D electronic transition making it colorless. Whereas in copper you have unpaired electron, so D to D electronic transition is possible, which gives blue color to this ion complex. Simply this is the keyword. You can write it down and you will get full marks. You get this question in your board examination to describe the general properties of transition elements for the 4 marks, in which you get 2 properties, or you may get this in the scientific reasoning for 1 mark. I will make a separate video for the important questions for chapter 2, so you can also watch that video for a better clarity of how you will be getting the questions for these topics. That is all for today. Thank you.